We are now going to look at a particular form of communication, in particular what's called the UART, right, the Universal Asynchronous Receiver Transmitter. Now, first we would like to understand what do we mean by communication and what is this requirement that we have over here, right. Let us assume that we have two systems, I am going to call them two processors, CPU 1 and CPU 2. And somehow I want to communicate some data between CPU 1 and CPU 2. Maybe I want to, I have measured some value, maybe a temperature sensor over here, and I want to send that information across to CPU 2 so that it can decide whether to turn on a fan or turn on a sprinkler or do some other kind of activity. I could have done that on CPU 1 itself, but maybe this is just a monitor and this is the actual central controller that takes care of things across a large number of devices maybe, right. Either way you can sort of imagine that the whole idea of transferring data between two systems could be useful, okay. Now what we are looking for is what's the simplest way by which I can actually send some data across from CPU 1 to CPU 2, right. So we would like to have something which is simple, and here is where one new term comes in, which is what we call asynchronicity, right, or an asynchronous communication. Now the reason for using this term asynchronous is one of the easiest ways for me to transfer data would be if I also had a signal over here called a clock signal, right, and what would that clock do? It would basically just keep toggling at a certain rate, and all that I need to do on the other side is every time the clock signal goes to either 0 or 1, I can basically specify that this is a 1 or a 0, and I would know on the other side that any time that I have some kind of a signal over here, I just need to look at this clock signal, I need to look at the data and I can pick it up. But what this means is I now have three wires over here. I have something to transmit the data, I have something to get the data back, I also need to send this clock, right. Now you might ask, why do I need a clock? After all, if I know that this is running at 1 megahertz and this is running at 1 megahertz, then I don't really need to send a clock between the two of them. The point is 1 megahertz is not 1 megahertz everywhere, right. It is nominally 1 megahertz, or we think it is 1 megahertz. In practice it might be 1.00001 megahertz, or maybe it might be 999.99 kilohertz. That's enough for these two to end up misreading the data that's been sent from one to the other. So rather than trying to sort of arrange for a common clock between these two, I would like to see, is there a way by which I can do this transfer asynchronously? That is, I don't need a clock, I just have some way by which I can send data out here and the other side knows how to pick it up, okay. And it turns out people came up with a protocol for doing this, right. There are a couple of problems you need to solve here, right. I am going to first look only in one direction. I want to go from CPU 1 to CPU 2 and I would like to do it just using one wire. Now straight away there is a problem there because one wire does not even form a closed circuit, right. In electronics you need a completed circuit for any change in voltages and so on to actually be visible at the other end, right. If I close a switch, it closes a circuit and then makes a light bulb glow somewhere, right. So what we are actually doing over here is we are going to implicitly assume that there is a second set of wires, a second wire between these two, which is just a common ground pin, right. So it doesn't have to, this by itself does not communicate any data, it just provides a common ground reference between both of these systems. But without that you can't really have this protocol working. So now I am trying to send data from CPU 1 to CPU 2, right. There are two problems that I need to solve. One is, how does CPU 2 even know when data has started coming in on this wire, right. It has to be able to look at the voltage on that wire and sort of sense whether is this new data or is this just nothing. It's not, CPU 1 is not trying to send data, right. In particular, if I always held this voltage as 1 volt or VDD, am I supposed to interpret that as CPU 1 is continuously trying to send me the data 1111, or is it just not sending anything? On the other hand, if I always hold this at 0 ground, then is it sending the data 0000 or is it just not doing anything? So there has to be some way to indicate when a communication starts and also what were actually the bits that need to be sent. So, the protocol that is used for this is something called a data frame is constructed, right, and the idea behind a data frame is we of course assume that we have a common ground reference signal between the two transmitter and the receiver, and then we say that that other line, the transmit line, which is going from the transmitter to the receiver, by default is going to be at this high voltage, right. The default ideal state is going to be a high voltage or VDD on the line. Now, whenever CPU 1 wants to communicate, it does something, it basically pulls that line low for a certain amount of time, okay. So, that's called a start bit. Immediately CPU 2 has some circuitry internally which detects the start bit and then says, oops, okay, now I need to start looking at the data coming in here, right. CPU 2 also needs to know the bit duration, that is how long is each bit supposed to be. Now, how do I get this information to CPU 2? I have to pre-program it. I have to tell CPU 1 and CPU 2, this is the speed at which you are going to program, at which you are going to communicate, right. So, as long as they both agree on it ahead of time somehow by some other means, right, CPU 2 knows that this is the duration of one bit. So, it sees this first duration of start and says, okay, this is not data, but it is telling me that data is going to come up after this. It then looks at the next bit out here and says, okay, now the voltage was high, it looks like a 1. It need not have gone high, right. If I wanted to transmit a 0, I could have just kept this as low voltage and CPU 2 would have picked it up correctly because it knows how wide the start is supposed to be, and after that it would know that okay, it is still 0, fine, the first bit was a 0, okay. But in this case I am sending a 1, 1, 1, then I send a 0, then again 1, then 0, 0, 1, 8 bits. Again CPU 2 needs to know that I am sending 8 bits, okay. And finally after all that I need to make this bit high, okay. Now, what if I didn't do that? I mean, in this case it turns out that I was already at a high voltage, so good news, maybe I can straight away go into idle mode. But this is an extra level of protection that we put in and say, look, you need to guarantee that after the 8 bits have been sent over here, the next bit is high, just to indicate that yes, this actually went through properly. When CPU 2 looks at this particular bit somewhere out here, and if it sees that the voltage was 0, it will actually think something went wrong and probably discard this entire transmission, right. So, you pull it low for 1 bit duration to indicate the start of a transmission. You then send 8 or whatever number. What I mean by that is, it is not always restricted to only 8 bits. 8 is the most common, but potentially you could send 5 bits or 6 or 7 bits. All those are also permitted and common, in fact, in at least in older scenarios. And then you need to have at least 1 bit interval when it is high to indicate a stop bit, meaning that I cannot start transmitting another piece of data right away over here. I have to go high at least for 1 bit to indicate a stop, and then maybe I could immediately go low to indicate the next start. That works, but you need to have at least 1 bit when it is high to indicate the stop. Now, in between this last bit and the stop bit, there are what are called optional parity bits, right, which can be used in order to detect errors. A parity bit, the idea behind a parity bit is simple. What it looks at is, it says, okay, how many ones did I transmit over here? 1, 2, 3, 4, 5, okay. Now, if I want to indicate even parity, I am going to send one more 1 over here in between this last one and my stop bit, so that the total number of ones becomes even. But if this was, let us say, 1 1 0 0 1 0 0 1, then the total number of ones is already even. I will transmit a 0 parity bit over here, right, to indicate even parity. Odd parity would be the opposite. I would try to make the total number of ones as odd. Now, why am I doing this? It basically says, look, there is a chance that because of some noise or fluctuations in voltage or whatever, one of these bits ended up being seen wrong. That parity bit will help me to detect whether there was an error somewhere out here. And if I see an error, what can I do about it? Nothing much, I just have to discard this entire byte, this entire piece of data. and maybe I can then send back information saying, hey, send that byte again or send that data again, right. But at least it allows me to make sure that if there is a small error over here, I can pick it up and cancel it. Now having said that, in a lot of cases we just skip it, we don't use parity, right, we just sort of leave it aside and say, look, I am not going to bother about this. Now the interesting thing is this data frame has allowed me to send data from CPU 1 to CPU 2. I have a protocol for how to start, I have a protocol for how to stop. If necessary, I have a protocol for how to provide a parity check, and I have this protocol for how to provide the actual data bits. What I need at the other end is just this information about the bit duration, and with that I can basically make sure that I sample all of these bits and get the values with some reasonable degree of accuracy, right. So the parameters that are required for this are usually specified something like this, and this is probably the most common set of UART parameters that you will come across. It says something like 8N1. What does this 8N1 refer to? In this case it means there are 8 data bits, no parity bit and 1 stop bit. Why did I not specify 1 start bit? Because 1 start bit is always guaranteed by the protocol. You don't have to specify it, there has to be 1 and only 1 start bit. Number of stop bits on the other hand can be changed, right. Again, why? It's part of some extra resilience that they want to build into the protocol. Again, the most common scenario is to have 1 stop bit and that's all. And the next parameter that you need to specify is 9600, which is the number of bits per second. It's also called the baud rate, which actually means the symbol rate, the rate at which symbols are changing on the wire, right. So you might sometimes hear this referred to as 9600 baud. What it actually means is 9600 bits per second, because that is the number of symbols per second that is transmitted. What's the difference? Well, there are other communication protocols where one baud or one symbol can actually transmit more than 1 bit, right. That's not the case in serial communication. So in serial communication, at least, we usually just interchangeably use the terms baud and bits per second. The more accurate term is bits per second, so it's usually preferable to stick to that. Or rather, that's the term that avoids confusion. It's not that it's more accurate, it just avoids any potential confusion later. So 8N1 refers to 8 bits, no parity, 1 stop bit, 9600 bits per second. The receiver must know all of these parameters correctly, else it will decode the data wrong. How do you specify those parameters? That's outside the scope of the protocol. You need some way of communicating it to the other end. Like I said, this is probably the most common, which means that a system could even start off by communicating at this speed, and then they could sort of transfer information that says, hey, let's switch to another higher speed now. But that's again outside the scope of what the protocol itself defines. So you can see that the core idea over here was simplicity, right? I mean, make the protocol as simple as possible, but of course you have certain limitations, which is that the fact that the receiver must know the parameters and that they should be sufficiently robust so that if there is a difference in clocks between the transmitter and receiver, it should still be able to pick up most of the data correctly, right? So, and more than that, there is overhead, right? Start bit, stop bit, both of those are not really communicating useful information. So there are different modes in which you can basically use the UART. By the way, this entire protocol is what's called the UART, Universal Asynchronous Receiver Transmitter. I have talked about the transmitter and also what the receiver does, right? There is also a version called the USART, the Universal Synchronous Asynchronous Receiver Transmitter, which has some extra logic in it to allow for some kind of synchronous transmission. For the most part, it is not very common. It is not the usual version of the protocol that's used, right? The UART is what is commonly used because of its simplicity. But what you actually have physically might be a USART, which is sort of a superset of what the UART can do and can still communicate with UART kind of peripherals. What about the modes in which this can work? You could have different modes of operation. There's something called simplex, which basically means I communicate only in one direction, CPU 1 to CPU 2, end of story. There is also half duplex, where I can go from CPU 1 to CPU 2. I can also transmit data back from CPU 2 to CPU 1, but only one of them at a time, right. Now there can be scenarios where this is done, but what is also reasonably common is to have full duplex, right. And the reason why this works is because I have a separate Tx and a separate Rx line. All that is important over here is the Tx from one side must go to the Rx of the other, and the Tx from the other side must come to the Rx of my first CPU or my first peripheral, right. As long as that sort of connection is taken care of, both sides can actually communicate. The transmit side and the receive side are more or less independent of each other. There are certain configuration parameters, in particular the number of data bits, the parity, the data rate. Up to 115 kilobits per second is commonly supported. There are sort of custom protocols that can go even higher than that, but as we will see later, right, I mean this is not really a protocol meant for high speed. So it is not typically used when you want to transfer large amounts of data at high speed. So why do people use the UART in the first place? Simplicity, right. It is a minimal amount of hardware. You pretty much just need 2 wires if the ground is common, right. You need 1 wire if you are looking at simplex communication. No clock synchronization is needed. It is very versatile, very widely supported. Because of the reasonably low speeds, it can even be emulated in software if needed. And there are, for example, FPGA cores that can be used in order to directly integrate this if you are creating your own custom logic or custom digital design on an FPGA platform. It is also, as you can imagine, very low cost. It has been around for so long and is so simple that there are like readily available sort of core designs that can just be included into your design and integrated as part of your digital logic. Now obviously it does not come for free, right. There are potential disadvantages. One of the most important would be the fact that it basically gives you lower data rates, right. And why does that happen? Because the system is basically sensitive to baud rate mismatches. If there is any difference in the baud rate specified on the two sides, you are pretty much off, you are losing all your data, right. Another sort of aspect that comes in over here is that higher speeds actually lead to problems when you are transmitting over larger distances. It is difficult to actually have a signal of toggling at a high speed and also covering a large distance of wire, right. There are variants of this, variants of the UART protocol that are sort of more robust and are meant for longer distances, usually using higher voltages and so on, but the basic protocol by itself is not very well suited for this. It does not have a shared clock, which makes it much harder to maintain timing, right, and if you have sort of drift between the clocks that are present on the two sides, you can end up with errors in communication. Normally a multi-master multi-slave configuration is pretty much not possible using this design. What do I mean by multi-master multi-slave? It is something like I have, let us say, multiple different devices, all of which are trying to communicate with each other. This is what is called a point-to-point design, whereas a shared bus would basically say, can I have something like this? This is sort of the intermediate point over here, and I would have the ability to communicate along any of these, right. So shared buses, basically there is only one wire coming out of each of these, whereas over here you can see that there are 2 wires coming out of each, which means that there are n minus 1 output wires if I have n blocks each trying to communicate with all the other n minus 1 elements, right. So multi-masters configurations are, multi-master multi-slave configurations are in general not possible, right, because it sort of requires the signal to be sent point to point in this case. There is a significant amount of framing overhead, the start bit and stop bit, and it has only a very basic form of error detection with pretty much no error correction capabilities. It can't sort of, even if it finds there is an error, all it can do is drop that byte and say send it, it can't even say send it again. Somebody else, some other part of the program has to somehow transmit data back saying, hey, send the data again, I lost it. There is a notion of something called signal integrity, which again is something which is not really in the scope of this course to consider, but is a very important aspect that as a system designer you need to be aware of. What signal integrity says is that how well does a digital signal or an analog signal that I have at a particular point travel across a wire, and how accurately can it be perceived at the other end, the receiving end, right. So, signal integrity becomes an issue, especially with longer wires or with lower voltages or a combination of the two, right. And UARTs are prone to running into problems when signal integrity is an issue. So, it is also potentially expensive in terms of CPU usage, meaning that it does not have a very sort of standardized way of handling data without the CPU being involved. The CPU has to be involved in each byte that is being transmitted and received. There are some ways of reducing slightly using interrupts, but it requires a fair amount of intervention from the CPU, more than what certain other protocols can provide. Now, a common use of the UART protocol is to provide what is called a console interface, right, and this is again a term that you are likely to come across, especially in terms of using embedded systems. The console is basically a text based interface that is used for primarily debugging, monitoring, configuration and control, right. It is not the most common form of interface for the end user, it is more for the developers, the people who are trying to build and debug a system. And because of the simplicity of the UART protocol, very often the console interface is a serial port, right. It is easy to implement, it requires minimal amounts of hardware, and it provides real time interactive execution. You can actually type in commands and debug the system using a very simple kind of a serial port hardware. Okay. And finally, one very interesting aspect of this, especially when you use it like a console, is the printf function that is present in languages like C, right. How do I implement something like printf? Now, printf has two parts to it. One of them is actually taking care of the formatting of a string, right, which means that if I want a %d, it should basically take the number and expand it out into a certain set of ASCII characters that represent the number. But the second part is actually taking those ASCII characters and getting them displayed on a screen. Now, an ASCII character is an 8-bit value, and UARTs can send 8-bit values. Well, yeah, they can send bytes, right, which means that they could potentially be used in order to send ASCII codes. As a result, in a lot of console applications, the reason why the UART is used as a console application is because the printf statement, for example, can directly be used in order to just communicate with the UART, right. And actually, the elegance of the way things are implemented is that you just have one function which is called _write, right, not the write function but _write, which needs to be implemented as a function in C. And as long as you write this function, printf will automatically call _write to send the individual characters, which means that you have basically taken your hardware abstraction to a point where, as long as you know how to perform _write, you are able to send one byte at a time, and you pretty much have the full functionality of printf and similarly of scanf available to you.